Welcome to week 2, where we will discuss energy flow through the atmosphere. In week 2, we will be discussing what energy is, how it behaves. We'll get into how solar energy drives the circulation of air and water in the atmosphere, and then we will discuss how temperature varies by location over time and what determines these variations. But in this video, we will talk about what energy is and how it behaves. So energy is the ability to do work. There's two primary states, kinetic and potential. We'll discuss that in the next slide. And there are a bunch of different forms. There's chemical energy, electrical, radiant, thermal, mechanical, and sound. And then one note is work is done when energy changes from one form to another. So for instance, from radiant energy to thermal energy, or chemical to thermal. So something has to be done for that change to occur. So the difference between kinetic and potential. Kinetic is energy associated with motion and work. So in this diagram, we see a driver driving up a hill. So that car is actually in motion, consuming energy, and then the opposite side of the hill, that energy is being released. So air temperature relates to kinetic energy, or average, which is kind of the average speed of the atoms or molecules in the air. So that higher temperatures, the molecules are moving faster. And heat is the actual transfer of energy from one thing to another through three processes: conduction, convection, and radiation, which we'll talk about in a few slides. And then potential energy is would be this driver at the very top of the hill, stopped at the very top. This object has the ability to do work, but is not currently doing work. So like a book on a shelf that could fall off would be a good example of that. So the three forms of transmitting energy from one object to another. We'll use heat for an example, would be conduction. So this is transfer of heat by random molecular collision. So we have a few examples over here. So we have a welder heating up using a welding torch. It's producing heat and then transferring that heat to the actual metal that is being welded. And then we also have an example would be if you put a pan on a stove. So the stove is producing the heat, it's transferring to the pan, which is then transferring to the food that you're cooking. So radiant energy, this is what we get from the sun. So this is the conversion of thermal energy to radiant energy. So we're heating something up, and then that object is then radiating heat through the air. And this is how energy gets here from space, or from the sun through space. And also, one thing that relates to radiant energy is taking a look at this example, we're going to do a similar thing like this in lab, where different objects will actually absorb more heat than others and reflect more of that radiant energy. So if you look at the surface of the Earth, white surfaces like ice is going to reflect that energy, whereas darker surfaces or water will actually absorb more. And here's just an example of Greenland. The darker blues, there is less albedo, so less of that material or that radiant energy reflecting. And then the pinks are more reflection happening off of that surface. And then convection is the actual transfer of heat by the motion of matter from one place to another. So for example, in a pan on a stove, you're boiling water. The water is going from the bottom of the pan to the top of the pan because it's heating up and causing a density difference, and we have that material starting this kind of rotating pattern. So here we've got material warming up, warming, density goes down, rises, and then it starts to cool, gets denser, and sinks. So this is how heat transfer occurs through fluids, gases, and solids that are capable of flow. So that's how we have clouds forming. We have the circulation that happens in the atmosphere. And then we have radiant energy. So this is the energy that actually reaches us from the sun, and it can take many different forms. and they're distinguished by wavelength and frequency. So on this electromagnetic spectrum that we see over here on the right, shorter wavelength, things like gamma rays, X-rays have a shorter wavelength. Towards the top where we have a longer wavelength, things like radio waves, microwave ovens, and then right in the middle, roughly in the middle, we have visible light. And everything that has a temperature will emit infrared radiation, including the Earth. And here's just a picture showing where we have more red colors are showing where we have warmer temperatures and more infrared radiation. Some of this escapes to space, some is actually absorbed by greenhouse gases in the atmosphere, and then they in turn increase in temperature, and then we have those greenhouse gases emitting more infrared radiation, kind of increasing the temperature over time. As you can see here, we've got the infrared radiation coming off of the surface of the Earth. Some of it gets trapped by these greenhouse gases, radiated back down or radiated toward each other, having this positive feedback loop. And this whole transfer of energy leads right into latent heat, which is the energy required to change a substance from one state to another. So when we look at water, which we're going to deal with quite a bit in this course, we have three phases: solid, ice, liquid, rain, and vapor would be clouds. So through this process, when we go from one thing to another, if we move to the right, this blue arrow, we are taking energy from the environment, whereas when we move to the left, we are releasing energy into the environment. So when we melt snow, we're taking energy from the environment in the form of heat energy. Same thing with evaporation. When we condense things, we are emitting heat to the environment. So we see this phase change back and forth. So for evaporation to occur, melting to occur, we need warmer temperatures. And to kind of relate to that, we have warmer temperatures or warmer air. The molecules, you can see these little Mickey Mouse guys, are going to be moving faster, bouncing off of each other and move further apart. So we get to the gas phase. And then when we have things decrease in temperature, the molecules don't move as fast, and then we end up having things getting closer together. And this is why cold air has a higher density, because you have more molecules in a smaller area compared to vapor, or a warmer air where things are further apart, so we have a lower density. And this temperature difference we measure in Kelvin, Celsius, and Fahrenheit, are the different temperature scales. You'll see in the news temperatures reported in Fahrenheit, but we are going to be looking at them in Celsius. And here's just another example of this heating up of water in a beaker or an Erlenmeyer flask here. It's cooler, the molecules are closer together, we heat it up, molecules get further apart, and it gets less dense. So that wraps up how energy behaves and what it is. Check your book for more details. We'll come back and talk about solar energy in the next video.